All right, how's everybody doing out there, remote learning land today? Today's hot topic, we're talking about calculating the eccentricity of ellipse, the measure of how flat an oval is, if you will. And of course, we're relating this to the orbits of the planets, right? They are not circular, they are oval-shaped, elliptical. And that's what we're looking further into today. If you look on the bottom here, you can see an eccentricity of 0 is a perfect circle, and as you increase your eccentricity, right, at 0.6, 0.8, it becomes more oval-shaped. You can't go greater than 1, and we'll talk about that. You also notice the position of the sun is at a different point, right? That's called a focal point, and we'll chat about that as well. All right, so without further ado, let's get rolling here. Hit pause on this, see if you can figure out which planet goes in which orbit. All right, so for the first one there, I am Planet X, made of rock, feels super hot, 100 million kilometers from the sun. Hopefully you put this toasty planet at the inner orbit here. That would be like Mercury. All right, for the next one, Planet Y, made of gas, a gas giant, a Jovian planet. Very cold, 1,430 million kilometers from the sun. Hopefully you put this guy way out there. That would be like Neptune, right? Or Uranus. There you have it. By the way, this inner one would be a terrestrial planet, like. And Planet Z, made of rock, feel warm, 230 million kilometers from the sun. That would be the most Earth-like, of course, right, in that Goldilocks zone. And there you have it. Okay, remember, it's not just the distance that affects the temperatures on Earth anyways, right? It's also the tilt of the axis. But when you're talking about these extreme differences in distance, then yes, that affects the temperature of that planet. Okay, so read it through. How do we define eccentricity there? All right, the measure of out of roundness of that shape. You'll notice here we have the sun at one focal point and another point out there in space. Don't worry about that point so much. This is the key one right here. This is the one that governs the orbit, right? The massive star, in this case the sun. So there's your definition of eccentricity, right? Out of roundness of an ellipse. The formula is in the reference tables. You don't have to memorize this, but you do have to know how to manipulate and plug in. So we'll start out with the distance between the focal points. Well, if you take a look, that's right here. Okay. Divided by the length of the major axis, well, that's going to cut through the two focal points, right? So your major axis is the longest diameter, if you will. The minor axis is here. We don't worry about that one, okay? So it's the distance between foci divided by the length of the major axis. And when you do that, you'll actually get a number between 0 and 1. You're going to use a ruler to manipulate your screen, of course, and we'll do a couple examples in a second. All right, before we jump to the math of it, take a look at the trend here, right? That's a 0.8. Look at the shape. There's a 0.6. Look at your shape. 0.4. 0.2. Look what's happening to that shape, folks. And, of course, a 0. Hopefully you realize it's become much rounder. Now we go the other way. There's a 0.2, 0.4, 0.6. Look how far out the sun is from the center point at this point, right? As you increase eccentricity, the distance between the focal points increases. And now we go back the other way. Your other focal point would be here, getting closer to center, and then all of a sudden, boom, a 0 only has the sun in the middle. You want to say they're overlapped. You can't see the other one. That's fine. But as you increase eccentricity, the distance between focal points increases and the shape becomes more oval shape. Okay? Here it is spelled out. There's a 0 eccentricity. That's a circle. 0.8 looks crazy oval shape. 0.9995. And if we stretched it even more, it would become a straight line. Right? So a line has an eccentricity of 1. There is no planet with an orbit of an eccentricity of 1. In fact, most planetary orbits you'll see on the chart are closer to 0 than any of these on here. Okay? Least eccentric to most eccentric going down. Okay, as the focal distance increased, so did the eccentricity. Eccentricity will always be between 0 and 1. If you get a calculation that's like a 2.7 or something, you did something wrong. You probably just divided it the wrong way, so recheck your work. Okay? Can't be less than 0, can't be greater than 1, obviously can't be negative. It's always going to be between 0 and 1. If the eccentricity is 0, you'll have a perfect circle. And if it's a 1, you will have a perfect straight line. Okay? All right, so get that into your notes. All right, here's the chart and the reference tables. We're very familiar with it. Which planet has the highest eccentricity? Well, go to your eccentricity column. Go down, find the one with the greatest value. Hopefully you came up with good old Mercury, right? Mercury at 0.206, the most elliptical orbit of our planets. It used to be Pluto, right? Pluto obviously got kicked out, and we spoke about that. Pluto used to be more elliptical. That was one of the reasons it got kicked out. Its orbit was too elliptical to fit the pattern. And again, they think that was more of a captured meteor, or asteroid rather. All right, then it says the lowest eccentricity. Well, again, go down for the lowest value, and boom, the goddess of love, right? Venus, only with a 0.007, almost a perfect circle orbit, but not quite. Okay? All right, so how do we calculate eccentricity? Well, there's our formula again, and like I said, you're literally going to have to take a ruler. Now, it doesn't matter how much you enlarge or shrink when you do this, but once you have enlarged or shrunk it to the point that you like, leave it alone, because you have to take both measurements from that perspective, from that enlargement. All right, so I'm not going to touch my screen. I'm just going to keep it the same for both measurements, as you'll see. My distance between foci, it looks like about 7.7-ish. And now I'm going to move the ruler without touching the screen to get my major axis, and I'm getting about 11.2-ish, right? If you look there, about 11.2. Notice I did not touch the screen. That would have changed the perspective between the measurements. That you can't do. So set it to where you want it, and then take your two measurements. Now I'm going to put them into the formula. 7.7 divided by 11.2, it's got to come out between 0 and 1, if you recall. And there it is, a 0.6875. All right, I'm going to round that to the nearest thousandth. That's what we often do. So if I round that, it becomes 0.6888, right? The 7.5 rounds up, and there it is. And those are the numbers you see on the chart, right? 3 numbers after the decimal. How is the eccentricity of our planet ellipse, this planet here, compared to Neptune? Well, Neptune is a 0.009. This is much bigger. Therefore, this is way more elliptical than Neptune's orbit, right? Right, this planet is way more eccentric or elliptical than Neptune. How about this question here? Can you guys put an X where the planet will move the fastest? Hit pause. Put an X where you think the planet will move the fastest in its orbit around the sun. All right, hopefully you chose closest to the sun, right? From our lesson the other day, the closer you are to the sun, the more gravitational pull you'll have, therefore the faster you're going to go. Okay? Let's do another one. Right there, explain that. Why will our planet move the fastest when it's next to the sun? So please jot your answer in there. The closer you are to something, the greater the gravitational pull. Okay? All right, hopefully you're good on that. Any questions, make sure you ask in the meet when we get there. All right, so going to do one more here. Calculate the eccentricity. So what you guys, of course, going to do, enlarge this to however you like and leave it alone. Okay? Then take your measurements. So I would get my ruler. Go grab my ruler right now. And I'm going to do my measurements, right? E equals D over L, distance between foci divided by length of the major axis. So I take my ruler. I don't touch the screen, right? I get as close as I can. Looks like I'm getting about 20 centimeters on my ruler. And now I'm going to measure the whole way, the major axis. And if I do that and shift over and adjust, right, I can't change my enlargement at this point because I've already taken my first measurement. I'm coming up with about a 56. Now, your numbers might not be the same, and that's fine. But when we divide, you're going to get the same answer. Okay, well, very darn close. All right, and when I do that, of course, I plug it in. So I got 20 divided by 56, all right? And I plug that into my calculator, and I'm getting about a 0.357. Hopefully you are getting something very close to that. Again, your numbers up here are probably different, but this should be about the same. How does that compare to Mercury's orbit? Well, go back to the reference table chart. You'll see that Mercury's orbit is definitely less than a 0.357. So you would say Mercury is less eccentric than the planet. Okay? Okay. So you guys have some other eccentricities to calculate, some summary questions, and of course we'll go through all that back in the meet. I'll see you then.